The 13th question says that find two numbers whose sum is 24. Okay, now some real life problems and some word problems which says two numbers whose sum is 24 and whose product is as large as possible. So you are interested in sum is 24 and product has to be maximized. Okay. Let the numbers are x and y. It is given that x plus y is equal to 24. This is given. And we are interested in the product function. Product is xy. Okay. Whenever you get this kind of a question, try to write this expression that you want to minimize or maximize. Write that expression in terms of a single variable. Single variable, here we are using two variables, right? Instead of two variables, let's convert this expression into a single variable, and that can be done with the help of this equation. Y can be replaced by 24 minus x, yes. So therefore, P is equal to x times 24 minus x, right? Okay. This is 24x minus x square. This is the product function. Product in terms of x, right? Okay. And now I can minimize, maximize this by simple differentiation, or since this is a quadratic, I can do that directly as well. Let's use the derivative. dp x by dx, that's a derivative which is 24 minus 2x equals 0 implies x equals 12. Now this is a critical point. X equals 12 is a critical point. Beyond 12 this is negative, before this is positive, this is increasing, decreasing. Do you observe that px will attain its maximum value at x equal to 12? So px max occurs at x equal to 12. What is that? 12 times 24 minus 12. What is that? 12 times 12, which is 144. That is my answer. The maximum product is this. So you are supposed to find two numbers whose sum is this and whose product is as large as possible. You are not supposed to find this product. You are actually supposed to find the two numbers. Numbers will be, one of the numbers is x, which is 12. The other number is y, which is 24 minus x, 12. That's my answer for this question over here. Is that all? Yes, that's the 13th question for us. The 14th question says find two positive numbers x and y such that x plus y is equal to 60 and xy power 3 is maximum. Okay, we are interested in this. So we want to maximize this, the product, or we can call this expression E. Let us say xy power 3 has to be maximized. Okay, this is the important thing. Try to write this in terms of a single variable. Okay, and how do we do that? X plus y is 60, so x can be replaced as 60 minus y. This is y power 3. Since x plus y is equal to 60, I can write x as 60 minus y. So this now becomes an expression in terms of y. Okay, and we want to maximize this. What is this equal to? This is 60 y power 3 minus y power 4. This is expression in terms of y. We can differentiate, use the first derivative, yes. So e prime y, differentiating with respect to y. That's what we are doing, right? Let's do that. Let's write it as d by dy of this, which becomes 60 times 3 is 180. Y square minus 4 y power 3. Okay, you can take out a y square common, you get as 180 minus 4y. This is what you get, right? This is what I'm getting. And what else? You could have taken out a 4 common as well, but this is 45 minus y. If you want to write the critical points will be 0 and 45 are the critical points. So beyond 45 this will be negative, this is becoming negative. Before 45 this is positive, and here also it is positive, since at 0 there is no sign change because of that y square. Okay, so function increases and then decreases. That's what you're interested in. Two positive numbers. Oh, so you're not supposed to go in this region anyhow, right? We are only dealing with positive numbers. Y cannot be negative. This and this is maximum. Find two positive numbers x and y such that this is 60 and xy cube is maximum. Maximum will occur at this point when y equals 45, ey is maximum. So that's the value of y. And what about x? And x equals, x plus y is 60, therefore x equals 15. And yes, that is my answer. X equals to 15, y is equal to 45. Answer for this question over here. The 15th question says find two positive numbers x and y such that their sum is 35 and the product, this is a maximum. Okay, a similar kind of a question. Two positive numbers x and y, x plus y is equal to 35, where x and y are greater than 0, and we want to maximize this. X square y power 5 has to be maximized. Okay, let the expression E is x square times y power 5. Let's eliminate one of the variables from this using that condition, and we can easily eliminate x. X is its lower power. This is 35 minus y whole square times y power 5. This is what you have, right? Since x plus y is 35, this is expression in terms of y. And the next thing that I'll do is differentiate this. D by dy of E y, and what is that? We'll apply the product rule first, and along with that the chain rule. So 35 minus y whole squared times, this becomes 5y power 4 plus y power 5 remains as it is. 2 times 35 minus y is what I get, and then the derivative of this is minus 1. 35 minus y, the derivative is minus 1. So you can take out something common. Yes, 35 minus y and y power 4. These are the factors that will come out common. This 35 minus y and y power 4 from these two will come out common. What will remain is 5 times 35 minus y and minus 1 times y. And there is a 2 as well over here. Please note this carefully. Right, you take out 35 minus y and you take out y power 4, 5 remains, 35 minus y remains. You take out 35 minus y and y power 4, y, 2 and minus 1 remain over here. Right, on the basis of this, further we can say that d by dy of Ey expression in terms of y is equal to 35 minus y is okay, y power 4 is okay. What is this equal to? This is 35 times 5 minus 5y minus 2y. So this becomes, okay, 5 times 35 minus 5y and minus 2y is minus 7y actually. So let's write it as 5 times 35 minus 7y only. Let's not multiply them together. I can take out a factor of 7 common now. 7y power 4, 35 minus y, and this remains 25 minus y is what I get over here. That's the expression. Okay, now let's mark the critical points, 25, 35 and 0. And you're not supposed to go beyond this because we are only considering the positive values, right? Let's analyze the sign scheme. Beyond 35, this is negative, this is negative, this is positive. Overall will become positive. Between 25 and 35, let's pick up 30. This is positive, this is negative, positive, this overall is negative. And before this, this is positive, 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 and therefore positive, this is positive. So function increases, decreases, and then increases again. Okay, find two positive numbers. This is such that the sum is this and the product is a maximum. So when is the product maximum? Do you see that the sum is 35, the maximum value will be 35. That's also interesting, right? Since the maximum value is 30, the sum is 35, therefore obviously x and y cannot go beyond 35. That's something that you should see clearly, right? So beyond 35 is also not something that you're interested in, and product is maximum at this point when y equals 25. The product is maximum. So y equals 25 and the other number x is equal to, since the sum is 35, this is 10. That's my correct answer for this question over here. That's the correct answer for this one. Right, so 15th is done, and that's the complete solution of this question. X and y, the values are 10 and 25 respectively. The 16th question says find two positive numbers whose sum is 16 and the sum of whose cubes is minimum. Okay, so let x comma y greater than 0 be such that x plus y is equal to 16 be the two numbers. Okay, the numbers will be, obviously since they are greater than 0, the numbers will be less than 16 as well, less than equal to 16 or less than 16 for that matter, and sum of whose cubes. So sum of whose cubes, let's talk about s is equal to x power 3 plus y power 3, and this is supposed to be minimized. We are supposed to find the minimum, right? We are supposed to find the two positive numbers actually, and for which this cube, sum of cubes is minimum. The first thing that we are supposed to do is, since we want to minimize this, let's convert this in terms of a single variable, and that can be done by writing x cube, y cube as 16 minus x power 3, right? This is s. This is actually s of x, as you can observe. Now we can differentiate. And this becomes s prime x is equal to 3x square plus 3 times 16 minus x whole square times minus 1. 16 minus x derivative is minus 1, right? This is what you get. Okay, and 3 can come out common. This is x square minus 16 minus x whole square. What is that? 16 square is 256. Minus of minus will become 32. X with a plus and minus x square is what I get. In the bracket, this goes. And you can take out a 32 common. 3 times 32 comes out common. What remains is x minus 2 power 5, 2 power 8. This is 8 actually. Okay, 2 power 3 is what you get. 32 times 8. Yes, this is what you get. So, that's the derivative. The only critical point is 8 that I get. This is 0, this is 16, right? So, beyond 8, this is positive, this is negative, this decreases and increases. The minimum value occurs at this particular point. Minimum of Sx occurs for x equal to 8. Okay. Find two positive numbers whose sum is 16 and the sum of whose cubes is minimum. That minimum sum of the cubes occurs for x equal to 8, y equals to again 8. That's what you have. That is my answer for this one over here. The 17th question says a square piece of tin of side 18 centimeter is to be made into a box without any top, by cutting a square from each corner and folding up the flaps to form a box. Okay. What should be the side of the square to be cut off so that the volume of the box is the maximum possible? We're interested in the volume of the box. Okay. Right. So square piece of tin. This is, let us suppose, the square piece of tin. Having side of 18 centimeter. This side is of 18 centimeter. Okay. And in mathematics, I've said this before, I'm saying this again, consistency with the units is important, right? Also that is important throughout, but we're not supposed to go in, let us say, SI units and all. If simple consistency is sufficient, right? Centimeter, if the length is in centimeter over here, everywhere, if the length is in centimeter, you're not supposed to worry about anything and you will get the correct answer. And after that, you'll be able to write the units as well, right? No need to worry about that too much. A square piece of tin of side 18 centimeters to be made into a box without top, by cutting a square from each corner. Square from each corner, okay? And folding the sides, folding the flaps, right? That's what you'll do. And it is not known that the sides of square the sides of square are not known. We're supposed to find this x and this x, right? Let side of this small square be x. Folding up the flaps to form the box. What should be the side of the square? This x is equal to question mark. So that volume of the box is minimum. Volume of box is maximum. Right? This has to be maximized. Right. So we'll write volume of the box in terms of that x somehow. And on understanding this complete shape, do you realize that the base of the box will be this? And this flap will be folded to give you this kind of a box over here. This is what the box looks like from the side. This x will be folded and this will become this height. The base length, what will this base length look like? These will be exactly same. The two base lengths will be exactly same. And what is this? This is actually this length, or which is equal to this length. You can clearly observe this, yes? This is total is 18 minus x is actually 18 minus 2x. This is 18 minus 2x. That's the base of the final box. This is 18 minus 2x. In this and as well as this direction, the height is x. Okay. And this is empty from the top, and the volume in this particular cuboid, this actually becomes type of a cuboid now. We're interested in the volume of the cuboid after this. Right. So can you observe that volume of box is LBH, since we are interested in the cuboid. This is length, this is breadth, and this is the height, x. So this is 18 minus 2x. 18 minus 2x times x. This is the volume of the box. Okay. This tells me Vx is equal to, okay, you can take out 2 common. This was 4 x times 9 minus x whole square. This is what I get. Volume of the box is this. Okay. And we want to maximize this. Is this in terms of a single variable? Yes. This is in terms of a single variable, so we can differentiate to maximize and minimize this. So let's differentiate d by dx of Vx. What is that? 4x is okay. This is 2 times 9 minus x. We'll apply the product rule, by the way. This is 2 times 9 minus x times minus 1 plus 4 times 9 minus x whole square. The derivative of x is 1. This is what you have, right? Okay. So where does that take us? Can you take out something common? Yes. I see a 4 coming out of common. I see a 9 minus x coming out common, and what remains in the bracket is 2x with a minus. This is minus 2x and plus 9 minus x is what I get. This is 4 times 9 minus x and this is 9 minus 3x. Okay. Critical point 3, critical point 9 are the two things that I get. 3 and 9 are the two critical points that you get. Okay. Do you observe that there's some condition between this? X should be greater than 0. Not only that, 18 minus 2x should also be greater than 0. Right? So 18 minus 2x greater than 0 would imply x will be less than 9, x will be greater than 0. So 0 and 9 are two endpoints. And if you observe, beyond 9, it will have some sign, but let's not go beyond 9. Let's go beyond 3 first of all on this side. So let's pick up maybe 1. This is positive, this is also positive, therefore this is positive, right? Beyond 3, if you go, this becomes negative, and beyond 9, if you go, this becomes negative. Sorry, this becomes positive. This is using the first derivative concepts. Increases, decreases, but we are only interested in this particular genre over here, right? Between 0 and 9. We are interested only in this, so that the side lengths do not become negative as such. And volume is maximum when x equals 3. That's the important thing. So Vx is maximum at x equals 3. Okay. And what should be the side of the square to be cut off so that the volume of the box is the maximum possible? This is the side length. And x is unit of length, right? And unit of length, as you can observe, is we have been using centimeters throughout. There was only one location at which the units were mentioned, and that is centimeter. Nowhere else were the units mentioned. Yes, everywhere else the unit will be in centimeters. So therefore, side of square required to be cut is equal to 3 centimeter, which is my answer for this question over here. That's a 17 question for you. Question number 18 says that a rectangular sheet of tin 45 centimeter by 24 centimeter is to be made into a box without top. Okay. By cutting off square from each corner and folding up the flaps, what should be the side of the square to be cut off so that the volume of the box is maximum? Now, question similar to the previous one, but herein we are starting with a rectangular sheet, not with a square sheet. But the diagrams and everything else will be pretty similar. What we have is a rectangular sheet of tin 45 centimeter by 24 centimeter. This is what we are beginning with. 45 centimeter by 24 centimeter, and you are cutting squares from the corners. Let's say the square side is x and x. Okay, x will be in centimeters, lengths will all be in centimeters, okay, and the base will be this. Okay, we'll remove these sides and we'll fold these flaps to give us a shape of this side, this type, right? This is the shape of the tin box. And this width, what will this width look like? This width will be equal to what? Do you observe that x and x will go, so this remaining width is this, and which is equal to this over here. This is equal to 45 minus x, which is 45 minus 2x. This will be over here. This is the width. Sorry, this is the length of this box. What about this one? This will again be 24 minus x, which is 24 minus 2x. The height will be this x only. This is x, x, x. This is the height, this tin box, right? And there's no top, there's no covering. Okay, so this particular edge can also be clearly visible. But, right, this is the kind of thing that will have. That's a box. Okay, so a rectangular sheet of tin 45 centimeter by 24 centimeter, box without top, by cutting the square from each corner, folding up the flaps. Okay, and what should be the side of the square? That is x equals question mark, so that the volume of the box is maximum. Volume is maximum. Let's maximize the volume. So first we'll write the volume in terms of a single variable. Volume of this particular box will be actually, this is a cuboid kind of a thing. This is length, breadth and height. What is that? 45 minus 2x times 24 minus 2x times x is what I get, right? This is what I'll be getting. And this can further be written as, maybe you can take out a 2 common, x common, for that matter, Let's multiply these together. We can also multiply them together, yes. Or since this is volume in terms of x, why not find the derivative and then see where does that take us? So let's find the derivative, dv by dx. What is that? This 45 minus 2x, this 24 minus 2x remains as it is. This is the third function. So we are applying the product rule, extended product rule. A, B, C, what we'll do is A, B constant, C derivative is 1, plus A constant, B constant, and the derivative of 24 minus 2x, which is minus 2, plus 24 minus 2x constant, x constant, and 45 minus 2x, the derivative is minus 2. This is what you get. Right. What is this derivative equal to? This derivative is a quadratic function. Let's simplify this as much as possible. 45 into 24 is what I get, which is a big number. This would be 90 times 12, which is 1080. Okay. Minus 90x and minus 48x is minus 138x plus 4x square is what I get. Then minus 2x times 45 is minus 90x, and minus 2x is plus 4x square. Okay. What is this? Minus 2x into 24 is minus 48x and plus 2x square is what I get. This is equal to what? This is equal to, okay, you get a 1080. Let's not begin with this 1080. Let's begin with the square terms. 4x square and 2x square. Is it? No, this is also 4x square actually. Minus 2x will become 4x square. That's what I'm thinking this. This is 12x square. Okay, then you have 90 and 148 and 138. It's like 90, 48 is 138, this is 138 again. So that will actually be 138 plus 138, which is 276x. This is what you'll get, right? Please check that. Yes, 276x. And the constant term is 1080. That's what you get. This is the quadratic function. Can we take out some things common? Yes, 12. This goes with 12. What about this one? Is this divisible by 12? 6, 7, 8, 8, 7, 15. This goes with 3. What about 4? This goes with 4 as well. So we can take out a factor of 12 common. This becomes x square minus 2 times 24, 3 times 36. Plus this is equal to 1290. This is what you get. This is what you get over here. Okay, that's a derivative for us. Can we factorize this and see where does that take us? So this is 18 times 5 and this is 18 and 5. This is 12 is okay. This is x minus 18, x minus 18, x minus 5. Okay, this is what is required. Right. And do you observe that this has to be positive, this has to be positive. So x should be less than 22.5, x should be less than 12 is important, right? And x should be greater than 0. Those are some conditions. So 0, 5, 18 and then there's a 12 as well, right? So we are supposed to deal only in this interval because of these restrictions. And what happens in this interval, right? Between 5 and 18, what happens between 5 and 18 is, this is positive, this is negative, so this will overall be negative. Before 5 this is negative, overall will be positive. Beyond 18 it will be positive, but that is not required. So in this interval the function increases and the function decreases. The volume maximum occurs for x equal to 5. The maximum volume occurs at x equal to 5. Max volume at x equals 5 centimeters. Centimeter is the unit. That's my correct answer. What should be the side of the square to be cut off so that the volume of the box is maximum? This is the side of the square that needs to be cut off for the volume to be maximum, as you can see over here. That's the complete solution. That diagram is important first of all. On the basis of this we can deal with this one, right? That's the complete solution of this 18th question. The 19th question says, show that of all the rectangles inscribed in a given fixed circle, the square has maximum area. Okay, so you're interested in a circle first of all, and within a circle you have a rectangle, and the area of the rectangle should be maximum. Let's consider the side lengths of this rectangle and see where does that take us. This is the rectangle, right? This is suppose the center of the square circle. Okay, if this is the center of the circle, then what will happen is, if this here is the center of the circle, what you'll get is, please observe, if this is, let's say, side of the square is x, side of the rectangle is x and y. Okay, and we are supposed to maximize the area of rectangle. Area of rectangle has to be maximized. That's what we're interested in, right? Of all the rectangles inscribed in a given fixed circle, the square has maximum area. So area of rectangle is important, and area of rectangle will be equal to what? Area of rectangle will be equal to simply xy. But this is two variables, right? We need to eliminate one of the variables and get a relation in terms of a single variable, right? How do we do that? Are we given some relation in x and y initially? No, not exactly, but then if you look closely, you are given something that of all the rectangles inscribed in a given fixed circle. So the circle is fixed, right? Circle is fixed means, what is fixed in a circle? Circle is fixed means the radius of the circle is fixed. This here is the radius, and this here is the radius. This is fixed basically. This throughout will be the diameter, yes or no? Yes. So diameter in this triangle over here, do you observe that this is 2r, this is x, this is y, and the diameter subtends an angle of 90 degree at any point on the circle. This is 90 degree. On the basis of this, you observe that from Pythagoras theorem, this is what you get. 2r whole square is 4r square. This is one of the relations between x and y. We can use them over here with this to get the area of rectangle in terms of a single variable. This tells me y square is equal to 4r square minus x square, and this tells me y is equal to, oh, should we take plus or minus? Y is a length, so we should only consider the plus, positive square root, since y is the length, okay? We'll take y equals to this. Therefore, area of rectangle is equal to x times under root of 4r square minus x square. Okay, now area has been found in terms of x. We can differentiate and see where does that take us. This is area in terms of x. So area of rectangle derivative is equal to under root of 4r square minus x square, product 2. This is differentiated 1 times this plus x constant, derivative of under root something, 1 upon 2 under root of 4r square minus x square. This is what you get. And what else? Derivative of this is minus 2x. Okay, this becomes, on taking the LCM, 2 times under root of 4r square minus x square. This becomes 4r square minus x square times 2 minus 2x square is what I get. Right? Do you observe this? So we can take out a factor of 2 common, and what remains is 4r square minus x square is minus 2x square upon 2 times under root of 4r square minus x square. This is important, right? At this stage, do you observe that x square is equal to 2r square is the important thing. X square is equal to 2r square. The critical point will be root 2r and minus root 2r. Okay, and this will tell me 2r and root 2r. So root 2r and minus root 2r are the two critical points for x from this expression. Okay, and if x is smaller than this overall value will be positive, and beyond this will be negative. Actually, this is negative. Using the first derivative idea, and 0 is something that is an important point, because x cannot be less than 0, right? X is a length, x cannot be less than 0. So we are supposed to deal only in this interval. The slope is positive, therefore this increases and decreases. So area increases initially and then decreases as you increase the value of x from 0 to some value, right? So maximum area occurs for x equal to root 2r, right? Maximum area implies x is equal to root 2r. And what does that tell me? What is the value of y? What is the value of y? Do you observe that? We can also find y, 4r square minus 2r square, which is root 2r again. Oh, this means that in the rectangle, therefore, x equals to y. The two side lengths, for maximum area, the two side lengths will be same, implies the rectangle is nothing but a square. This is square. Right? Hence proof. That's a complete proof of this question over here. The 20th question says, show that the right circular cylinder of given surface and maximum volume is such that its height is equal to the diameter of the base. Okay, right circular cylinder of given surface and maximum volume. Right circular cylinder will look something like this. This is what it will look like, right? It will be dotted. This is what a right circular cylinder looks like. This is center of this circle, this is the center of this circle, join them together. And the important thing is this height over here, one thing, this is the radius of the top or of the base, we can take it thus. Right circular cylinder of given surface area. Okay. Surface area is given, right? Surface area is fixed. This is given. And maximum volume. Volume has to be maximized. Okay. Such that its height is equal to the diameter of the base. So there will be some relation between H and R with the help of this. Volume has to be maximized, so we'll have to write the volume in terms of a single variable. But what is volume of this cylinder? This is pi r square h. Oh, there are two variables involved. How can we eliminate one of the variables? There should be some condition given. Yes, there's something fixed. What is that fixed? The surface area is fixed. Okay, if the surface area is fixed, where does that take us? So surface area can be handled in this way. Surface area will be equal to, what's the surface area? This is curved surface plus top and bottom surfaces. Top and bottom surfaces are pi r square, 2 pi r square plus 2 pi r times h is this curved surface area. This is what you get. Total surface area will be this, and this has to be, this is fixed. So we can, what we can do is 2 pi r plus h is actually fixed. Okay, this is given, right? So s fixed, and what you get is s is equal to 2 pi r times r plus h. Since s is fixed, we can take it as a constant, and we get one relation between r and h. Again, we can eliminate either r or h from here. H, you can see, is very easy to eliminate. This will tell me h is equal to s upon 2 pi r minus r. Minus r. This is the value of h that you will get. Right? Please note that. This is the value of h that you will get. Therefore, volume in terms of r will be equal to what? This is pi r square times h, which is s upon 2 pi r minus r. This is what I am getting. Right. Where s is a constant, pi is also a constant. And let's multiply them together. Where does that take us? This is pi gives s upon 2. R square upon r is r. Right? Pi goes s upon 2. This minus this is pi r power 3. This is what you get. Volume in terms of r. And we can differentiate d by dr of Vr. This is what we are interested in. So that we can maximize this. This is equal to s by 2 minus 3 pi r square. Okay, this is what you get. And this derivative tells me that, okay, d by dr Vr is equal to this. We can find the value of r for this particular thing equal to 0. R square will be equal to s upon 6 pi, which tells me r is equal to under root of s upon 6 pi. We should not take minus because r is a positive quantity. We will only consider the positive value. This is the critical point, r equals to this. Okay, what will happen for this particular case? Let's see. We can analyze using the first derivative, or for that matter, what we can do is think of it in this manner, that the volume will be either maximum or minimum at this point. Yes, for r is equal to this, the volume will be either maximum or minimum. If r becomes very, very small, then since the surface area is a constant, what will happen is height will become very, very large, but r becomes very, very small. In that case, the volume will also become very, very small. The volume will be very, very small, that is close to 0, right? In another case, what will happen is, if the r increases to a very huge quantity, the height will have to decrease to adjust for the surface area, right? Since the surface area is fixed. The volume in that case will also be very, very small, right? So volume increases and then decreases, right? That's what happened. At the extreme ends, the volume is very, very small. Somewhere in the middle, for some particular value of r, the volume will be maximum. So for this r, the volume is maximum. V max for r equals under root of s upon 6 pi. This is what we are interested in. Height is equal to the diameter. Oh, we are also interested in the height. Yes. Let's talk about the height. What is the height equal to? Therefore, height is equal to, okay, this is s upon 2 pi r minus r. This is s minus 2 pi r square upon 2 pi r is what I am interested in. What is that? S minus 2 pi times r square. R square is equal to s upon 6 pi. okay, upon 2 pi. What is r? R is under root of s upon 6 pi. This is what you get. Okay. On simplification, where does that take us? This is okay. This is 1 by 3. S minus s by 3 is 2s by 3 in the numerator. And in the denominator, you get 2 pi and root s. So 2 pi, let it remain as it is. Root s, let it remain as it is. And root of 6 pi is what I have over here. Let's simplify this further. Let's simplify this further. And what does that where does that take us? Root s is what I will be getting. 2 goes with 2. In the denominator, you have 3 pi. And denominator is denominator, root 6 pi will come in the numerator. This is what you get. Okay? This is 3 pi. Root 6 pi s upon 3 pi is what I get. Root 6 pi s upon 3 pi is what I get. And height is equal to the diameter of the base. This is what we wanted to prove, right? What is the relation between height and radius? Okay, so height in terms of this, can I replace root s by root 6 pi into r? Yes, this is root of 6 pi upon 3 pi times, this is root s, which is root 6 pi times r, which is 6 pi, root of 6 pi will be 6 pi, upon 3 pi will be 2, this is 2r, this tells me h is actually equal to 2r. This is for the case of maximum volume. The height will be equal to 2r, the height will be equal to twice the radius, which is the diameter, and that is what we wanted to prove in the original question. Yes, therefore for V max, r is this, h is this, which simplifies to 2r, and yes, that's the complete proof of this one over here. Show that, right? That's the 20th question for us over here. The 21 question says, of all the closed cylindrical cans, okay, cylindrical cans, right circular, of a given volume of 100 cubic centimeters. Okay, we are interested in closed cylindrical cans. This is a cylindrical can. Circular base, circular top, and this is right circular. Yes, this will be center, this will be center, this will be the radius, this will also be r, this is the height h. Okay, of all the closed cylindrical cans of a given volume, okay, volume is fixed in this case, V is fixed, of 100 cubic centimeters, V fixed, and it is equal to 100 centimeter cube. Find the dimensions of the can which has the minimum surface area. Okay, surface area has to be minimum. Okay, so we are supposed to write the formula for surface area and we are supposed to minimize that. Okay, minimum surface area. Find the dimensions of the can which has minimum surface area. There's only one place at which the unit is mentioned. So everywhere else, this will be in centimeter, this will be in centimeter, this will be in centimeter square, will be consistent with the units, right? That's the important thing. Volume is pi r square h. Okay, surface area, let's call this S. S is equal to 2 pi r square plus 2 pi r h. Okay, and if you want to differentiate S, because we want to minimize this S, so we'll have to write S in terms of single variable. Let's eliminate one of the variables with the help of this. This is equal to 100, by the way, right? So that tells me h is equal to 100 upon pi r square, right? This is what is known. This becomes S of r is equal to 2 pi r square plus 2 pi r times h, which is 100 upon pi r square. Can we simplify this further? This is 2 pi r square plus 200 upon r is what I get. Do you observe this? This is what I get, right? 200 upon pi. Pi goes 200 upon r is what I get, right? This is S of r. So derivative of S of r, what will that be? This is 4 pi r and minus 200 upon r square is what I get. And derivative equals to 0 will give me some particular value of r, right? So, which tells me S prime of r is equal to, in the denominator you get r square, in the numerator you get 4 pi r cube minus 200. 4 common, pi r cube minus 200 upon 4 is 50. Is what I'll get, right? This is what I'll get. And if you observe, right, what you'll guess is r is equal to, r cube is equal to 50 upon r is the critical point, which is 50 by r raised to power 1 by 3. The value of r, critical point is r equal to 50 upon pi raised to power 1 by 3. There's only one critical point, right? So either a maximum or a minimum will be occurring at that point. Let's analyze the question for a bit. What do we see? Volume is fixed, okay? If the volume is fixed and we decrease the value of r, so overall height will increase, the surface area will increase, the volume will be 100, will have to be maintained 100, right? So overall the surface area will increase, right? Since you'll have to increase height by a huge quantity. If you decrease the height, what you'll get is you'll have to increase the radius, and again you'll get a huge top surface, bottom surface, a huge area for that matter, right? So if we take extreme values of r, what you'll get is huge amounts of area. But then this is a critical point, right? So at this critical point, if the area is huge at this extreme, it has to be minimum at the center extreme, right? So SR minimum occurs at r equals 50 upon pi raised to power 1 by 3. That's what we get, right? So r has been found, and what will be the value of h? H will be equal to what? H is 100 upon pi r square. So therefore h will be equal to 100 upon pi times what is r square? R is 50 upon pi power 1 by 3, and it will become power 2 by 3, right? Okay, here you have a pi and here you have another 50. Let's write it as 2 times 50 upon pi. Okay, and in the denominator you have, it is actually pi by 50 raised to power 2 by 3. Do you observe that pi power 2 by 3, pi power 1 will get cancelled. You will get pi power 1 by 3 over here, and 50 power 2 by 3, 50 power 1 will get cancelled. So this will become 50 upon pi raised to power 1 by 3 over here. That's the value of h that is required. And yes, find the dimensions of the can which has a minimum surface area. This is the value of h and this is the value of r, for which you have minimum surface area. What about the units? So units, we have been consistent with the units. Everywhere will be here using centimeters. So this is in centimeter, this is also in centimeters, and that's the correct answer for this question number 21 over here. 22nd question says that a wire of length 28 meters is to be cut into two pieces. Okay, 28 centimeter wire. One of the pieces is to be made into a square and the other into a circle. Okay. So you get a wire of 28 meter. This wire is of 28 meter from here to here. Cut it into two pieces. Okay, one of the pieces, let us say this is x meter and this here is y meters. Okay, length is meters throughout. Let us ensure that length will be in meters. One of the pieces is to be cut and made into a square and other into a circle. Okay, this x will be converted to a square and this y will be converted to a circle. What should be the length of the two pieces so that the combined area of the square and the circle is minimum? This is A1 area, this is A2 area. Mind you, the perimeter is x. The perimeter is, that is the circumference is y. That's the limitation between these two, right? And combined area of the square and the circle is minimum. A1 plus A2 has to be minimum. That's the target. That's the target. Okay. So let's begin with this, right? And where does that take us? If x plus y is 28, that's the first thing. X plus y is equal to 28, that's one of the conditions. What about A1? For finding A1, we are interested in this square, and if the side length is A, then 4A is equal to x. Okay. A1 will be equal to A square, which is equal to x by 4 whole square, which is x square by 16 actually. This is A1. For A2, we have this circle, right? And if this radius is r, then the total circumference will be equal to y. This is 2 pi r will be equal to y, which tells me that A2 will be equal to pi r square, which is the area of circle. R will be y upon 2 pi. This becomes pi times y square upon 4 pi square. This is A2 for us. So we have found A1 and A2. Yes, we can add them and they maybe think of minimizing that area, right? Combined area of the square and the circle is minimum. And how do we do that? Area can be written in terms of sum of these two, but there are two variables involved, x and y. Okay, can we eliminate one of the variables? Yes, maybe we can eliminate this y and see where does that take us, or we can eliminate this x and see where does that take us. So a in terms of y will be equal to, x can be written as 28 minus y whole square upon 16 plus this is y square upon 4 pi. That's what we have over here. This is area in terms of y. Next we'll differentiate this area with respect to y and see where does that take us. So a prime, what we'll have is a prime y will be equal to what? This is equal to 2 times, this will become 1 by 8, 28 minus y and times minus 1. Okay, what will this be? Y square upon 4 pi, this will become 2y upon 4 pi. This is what you'll get, right? And can we take the LCM, get the value of y from here? Yes. The LCM will be simply 4 pi into 8 will be 8 pi actually. Okay, this will become 2 times 2, 4y, and this as a minus, this will be minus pi times 28 minus y. Okay, pretty interesting. Okay, and what else? What else? This will become plus pi y 4y. So 4 plus pi times y minus 28 pi is what I am looking at. This is 8 pi. Okay, and this equal to 0 implies y will be equal to 28 pi upon 4 plus pi. This is the value of y. And what happens at this particular value of y is, please observe, if you have, let us say, y equals 0, let's say y is very, very small, then you'll have complete square and 2 circle, right? So this is the area that you'll have. But in another case, let us say if y is maximum, x is least, you'll have only a circle and no square. And in all of those cases, combined area of the square and circle will be maybe greater, right? We are looking at minimum, and yes, this should be the value at minimum, although we'll have to check further. But considering this a prime y is equal to this, can we also find, let us say, a double prime y? Yes, a double prime y, that's a double derivative. Oh, we are using second derivative. Yeah, this is probably the first time we are using the second derivative over here. And this here is 4 plus y upon 4 plus pi upon 8 pi, and which is greater than 0. Okay, this is greater than 0 implies this will be point for minimum, right? This will be this is critical point which will be for minimum. Yes, the area will be minimum for this. What should be length of the two pieces so that the combined area of the square and circle is minimum? Therefore, the required, this is minimum for y equals 28 pi upon 4 plus pi, and x equals what? X equals what? X will be equal to 28 minus this. So 28 pi minus 28 pi will go, 28 times 4 is what will come over there. What's 28 times 4? This is 112 upon 4 plus pi is what I'll get. That's the other values. So for the square, the length will be 112 upon 4 plus pi, and for y, the length will be 28 pi upon 4 plus pi. That's my correct answer for this question over here. That's 22. Let's talk about 23rd question. The 23rd question says, prove that the volume of the largest cone that can be inscribed in a sphere of radius r is 8 by 27 of the volume of the sphere. Okay. Volume of the largest cone. We are describing a cone in a sphere of radius r. So sphere in 2 dimensions will look like this, and a cone will look like this. Right? Within the sphere, the cone will be this. This will be the cone. Okay. This is the center of the sphere, let's say. Okay. So important things, volume of the largest cone, volume of cone has to be maximized. This is important. So we'll focus on finding the volume, writing the volume of cone in terms of a single variable first, and then go for differentiation. Inscribed in a sphere of radius r, the radius of the sphere is r. This is r, okay. Is 8 by 27 of the volume of the sphere. So we are interested in volume of the sphere. Volume of the sphere is given for in terms of r, right? And what about this cone? This cone will depend on this cone. The height and radius are the two important things, right? The height and radius. Let's talk about the radius and the height. There will be some relation between the radius and height. And yes, what is that relation? This here is the radius r of the cone, and this here is the height of the cone. Yes, and do you observe that both of these will form a right angle triangle over here? So what do we have? this is the height, this is the radius for the cone, that's okay. And how can we find a relation between h and r? Can we find a relation? Yes, maybe. So observe that this is not related to anything. You can observe this is r, this is h, this complete big triangle, we don't have anything actually over there. But if you join this center with this endpoint, okay, this is endpoint of sphere as well. So this is capital R. And if you take a look at this triangle, this is capital R, this is small r, and what is this? This length. This is total h minus r. This is total h minus capital R. And that is one of the relations between, that gives us one of the relations between small h and small r. Okay. Volume of the largest cone that can be inscribed in a sphere of radius r. So we are interested in volume. Volume of the cone will be equal to what? This is 1 by 3 pi r square h. Okay. And for finding h, we have one relation, and what's that relation? H minus capital R squared plus small r square is equal to capital R square. This tells me that there are two possibilities. You can find r square from here and substitute it over here, or you can find h from here and substitute it over there. So eliminating r square seems a simple proposition, right? Let's do that. Vc in terms of h will be equal to 1 by 3 pi h times small r square, which is capital R square minus h minus capital R whole square. This is what you have, right? And now we can differentiate V h with respect to h. Where does that take us? 1 by 3. This will become pi, and h, this is r square is gone, derivative 0. We're applying the product rule. This times derivative of this plus this times derivative of this is what we'll do. So r square is gone. This becomes 2 times h minus r. The derivative of h is 1 after that. This is what you get. Plus the other term will be pi by 3 times derivative of which is 1 and times this huge bracket over here. This huge bracket will come over here, right? Okay. And can we simplify this? Yes. What do we have? This is pi by 3 h with a minus. So let's write this properly. This is minus 2 pi by 3 h times h minus r, which is h square minus r h over here. This is what we have. And plus pi by 3 times this whole thing. What is this? R square minus h square minus r square and plus 2hr is what I get. Okay. Can we simplify this further? Yes. We can take out a factor of pi by 3 common throughout, and this term will come ahead of that term. This is 2hr minus h square. Pi by 3 goes minus 2h square and plus 2rh is what I get. Can you observe that? Yes. This is what you will get, right? Minus to minus will become this. This pi by 3 is okay. In the bracket, what you get is hr 4 hr minus 3h square is what I get, right? I take out an h common. This will look like pi by 3 h times 4r minus 3h, and the critical points will be h equals 4r by 3, h equals 0. You can observe that h equals to 0 would imply that if this becomes 0, the volume of the cone will be minimum, and if h increases beyond a certain point, you will also get again the volume of the cone will be minimum. So if the volume of the cone has to be maximum, the critical point this h equals 4r by 3 gives me the maximum volume. This gives me the maximum volume. That's what you can observe over here. Okay. Once you observe this much, h equals 4r by 3. Can you find that maximum volume? Yes. Let's try to find that maximum volume somehow. And for that, what I'll do is I'll get rid of that left hand side. Let's get rid of all of this over here. Okay. And after that, we'll solve it further and see where does that take us. We have all the formula and all the values over here only. Let's try to solve this further. Vc has to be maximized. Okay. H is 4 times capital R by 3. What's the value of small r? Can I find small r with the help of this? Yes. Small r square will be equal to capital R square minus h minus capital R whole square, which is 4r by 3 minus capital R. 4r by 3 minus capital R, which is r by 3 whole square. This is r square by 9. Okay, r square minus r square by 9 is 8 r square by 9 This is what you have, right? Small r square is capital R, 8r square by 9. Therefore, volume of cone will be equal to what? Volume of cone will be 1 by 3 pi r square is 8 by 9 r square. Okay, h is 4 by 3 r. And can you please observe that this will become 8 by 27, let's multiply them together, times 4 by 3 pi r cube is what I get. 4 by 3 pi r cube is the volume of the sphere, right? So this is 8 by 27 times volume of sphere, if you may observe this carefully. This is volume of sphere, right? 8 by 27 times volume of sphere. The volume of the largest cone that can be inscribed in the sphere of radius r is 8 by 27 times the volume of sphere. That's a complete proof of this question. We have skipped that diagram. That diagram was there initially and we have erased that diagram, but this is the complete solution for this question over here, right? The 24th question says, show that the right circular cone of least curved surface area and given volume. Okay, right circular cone of least curved surface area. This is what a right circular cone looks like. This is the radius and this here is the height. Okay, root 2 times the radius of the base. Right circular cone of least curved surface area. Curved surface area least. Okay, we are supposed to minimize this curved surface area. And given volume, volume is fixed. Okay, has an altitude equal to root 2 times the radius of the base. To prove altitude is equal to root 2 times r. This is what we are supposed to prove, right? For least curved surface area. Okay, what about the volume? Volume is 1 by 3 pi r square h, and this v is fixed. We can deal in terms of v. Right? Curved surface area, let's call this C, curved surface area, and what will that be? This is pi r l. That's the curved surface area, right? This is a slant height L, and L is under root of h square plus r square. This is pi r under root of h square plus r square. Now let's see how can we eliminate one of the variables. What do we have? We have r, h and r square as well, and we have r square which can be easily eliminated, but there's another r as well, and how will we eliminate that? Okay, we'll have to write the under root for that matter, or indirectly can we say that we can eliminate h maybe easily? Yes, with the help of this one, maybe we can do that. Let's see, this is curved surface area. What is that? Equal to pi times under root will have r square h square plus r power 4. Let's take this r square in the under root. This will become r square h square. Okay, r square times h square. H square will be 3v upon pi r square and whole square. Whole square. Okay. Plus, what is this? This is r square is already there. One more r square, it will become r power 4. This is what you will get. Okay, huge quantity in the under root. This will become pi times. Okay, what will this simplify into? Under root of this is r power 4 plus what is this? R square upon r power 4. In the denominator you will have r square. So this is 9v square over pi square r square in the denominator. This is what you have, right? And right circular cone of least curved surface area, we have to minimize this quantity. Okay, if you want to minimize this whole quantity, then we can minimize this under root quantity as well, right? And we can get this. Let f of r is equal to r power 4 plus 9v square over pi square r square, and find the derivative of r. What you get is 4r cube. Okay, and 1 upon r square, the derivative is minus 2 upon r power 3. So this becomes minus 18v square over pi square r power 3. This is what you get, right? And equating this to 0 will give me r power 3 equals something, right? This will tell me that you can say 4 pi square r power 6 minus 18 v square is equal to 0, which tells me r power 6 is equal to 18 v square upon 4 pi square. This is it. Okay, this is r power 6, mind you, and this is only critical point. Will this give us the least curved surface area? Yes, volume is fixed. Okay, volume is fixed. So in case you will increase maybe r, what you'll get is you'll have to decrease this height, right? Okay, since the volume is fixed, but the surface area will increase. As you can see, the surface area will increase. This will be very, very huge cone. Small height. Since the volume is fixed, the surface area will have to be very, very huge. This radius of the base will be very, very huge. Okay, and that will be peak of curved surface area. What else? If we reduce the R by quite some value, then what we'll have is a very tall cone, so that the volume is fixed, and in that case the curved surface area will be again huge. This length will be huge, and in that case curved surface area will again be huge. So minimum value occurs at some middle point, and that is a middle point at which the curved surface area comes out to be least. R power 6 equals to this. But this is one part of the solution. Further, we have to go ahead and as an altitude equal to root 2 times the radius of the base. We are interested in the altitude for this R power 6 as well. Okay, and we are supposed to prove this one. So can we find h somehow? Yes, we can find h with the help of this maybe. This is 3v upon pi r square. H is already known to us. H is 3v upon pi r square. This is pi r square, but we need r power 6, yes. So why not deal with h power 3 first? H power 3 is, this is power 3, this is 27 v power 3 pi power 3 times r power 6, which is 18 v square and 4 pi square. What will this give me? H power 3 is equal to what? This tells me that h power 3 will be 27 upon 18, which is 3 by 2, and you have a 4, 3 by 2 into 4 will be 3 times 2, 6. 6 is what I'll get. V cube upon V square will be V, pi cube, pi square will be pi in the denominator. Anything else? No, this is what you'll get. H cube will be equal to this. Okay, and what is the value of h upon r? Therefore, h upon r will be equal to what? H upon r, h is cube root of this, 6v upon pi raised to power 1 by 3 is what I get. And r in the denominator will be ratio of this, 18 v square over 4 pi square power 1 by 6. This is what you'll get. This is what you'll get. Pi square power 1 by 6 is pi power 1 by 3. Pi power 1 by 3 will go. V square power 1 by 6 is v power 1 by 3. V power 1 by 3 will go. This gives me 6 power 1 by 3 times 4 by 18 is 2 by 9 power 1 by 6 actually. This is, or you can say that, you can simply say that this is, instead of 4 by 18, we can say this is 2 by 9, or further, can we deal with it in another way? Maybe? Okay, let it be. This is 2 power 1 by 6 over 9 power 1 by 6, which is 3 power 1 by 3. 3 power 1 by 3. Okay, and this further becomes 2 power 1 by 3. 2 power 1 by 3 times 2 power 1 by 6 is what we have. And we can add the powers, right? 1 by 3 plus 1 by 6 will be equal to what? This is 3 by 6, which is 1 by 2. So this becomes root 2. And h by r is equal to root 2 implies h equals to root 2r. This is what we wanted to prove. That's the proof of this complete question over here. That's the 24th question for us. The 25th question says that show that the semi-vertical angle of the cone of maximum volume and of given slant height is this. Volume is to be maximum, the cone is given, slant height is important, this height is important, this radius is important. Okay. Semi-vertical angle is important, this theta. Of cone of the maximum volume, V max. And of given slant height, L given. L is given. And semi-vertical angle theta is question mark. That is important, right? Okay. Since L is given, we can deal with H and R. H will be equal to L cos theta by simply this right angle triangle. This is 90 degree. R will be equal to L sin theta. This is simple, right? If volume has to be maximized, so V can be written as 1 by 3 pi r square H, and we can write V in terms of theta so that we can find that theta. This becomes 1 by 3 pi r square is L square sin square theta. This is L cos theta. It becomes L cube sin square theta times cos theta. This is what I am getting, right? And since we have V in terms of theta, can we differentiate to get, let us say, V maximum? Yes. So let's differentiate this sin square theta times cos theta. And where does that take us? dV upon d theta is equal to pi L cube upon 3 times this. This is sin square theta. And the derivative of cos theta is simply minus sin theta plus 2 sin theta. Cos theta is the derivative of sin square theta times cos theta is what I get over here. This is in the bracket. Pi L cube upon 3 is what I have. And what about the brackets? This is 2 sin theta cos square theta minus sin cube theta is what I get. Okay. And maybe we can take out sin theta common, and what remains is 2 cos square theta minus sin square theta. So pi L cube by 3, or alternatively we can also convert this cos square theta into 1 minus sin square theta and see where does that take us. So this is 2 sin theta minus 2 sin cube theta, and this becomes 3 sin cube theta. Okay, and that will give me some value of theta, right? So equating it to 0 will give me sin theta equal to 0, or sin theta is equal to 2 by 3. Sin square theta is equal to 2 by 3. Is that? Yes. Sin square theta is equal to 2 by 3. This is what we have. Right? And this is the important thing. Sin theta equal to 0 implies theta will be equal to 0. We'll get a very, very compressed cone, and if L is given, if L is fixed, then in that case the volume will be 0, very, very close to 0. That will give us a minimum volume. Either this and in the other case, since this is another critical point, if for this volume is minimum, for this the volume will be maximum. That's what you can say. And yes, we are interested in that maximum volume. We are interested in that maximum volume. Yes. V max for sin square theta is equal to 2 by 3. This is important. But then we are interested in the angle in terms of tan, right? If sin square theta is equal to 2 by 3, what is the value of cos square theta? Cos square theta is equal to 1 by 3. And with the help of this, tan square theta will be equal to what? The ratio of 2, which is this. And this tells me tan theta will be square root of 2. Oh, why not minus the square root of 2? You can observe that the slant, the angle, semi-vertical angle between 0 to pi by 2. That's the first quadrant, and this tells me theta will be tan inverse root 2 for maximum volume. That's the required answer over here. For maximum volume, this is what you get. That's the complete solution of this question, question number 25th. The 26th question says that show that the semi-vertical angle of right circular cone of given surface area and maximum volume. Okay. Semi-vertical angle. We are interested in semi-vertical angle. Yes, right circular cone and given surface area and maximum volume is what we are interested in. Okay. Now, if you focus on the semi-vertical angle, what is this? This is, let us say, theta. Theta is question mark, and given surface area is fixed, and volume has to be maximized. Okay. So volume has to be written in terms of one particular variable, and which variable can we use over here? Let's say this is H, this is R, okay, and this will be L. Oh, there are so many unknowns, so many variables, yes. But we have only one surface area, and that is fixed. So at max we can eliminate one variable from here. What is the formula for V? V is 1 by 3 pi R square H. So we'll maybe eliminate R or H, one of the things from here. And what is the relation between this? So let's not involve theta, because theta is not involved in this also. Let's not increase our calculations. Let's simply involve H square plus R square is equal to L square. And why is this involved? Because in the surface area, this L is involved. Surface area will be equal to pi R square plus pi RL, which is pi R plus L. Oh. And this L is known to us, right? This L is known to us. This is actually, you can please note this as, this L will be equal to what? This is pi R square plus pi R, and L will be under root of H square plus R square. This is what I have, right? S is equal to this. Can you please note that? Yes. And which of these variables is easy to eliminate from here? Can you observe that maybe I can find H maybe from here and can be eliminated over here, or I can maybe find R square if possible. We'll have to do some calculations and see which of these values can be eliminated, okay? Oh, okay. So let's do some calculations over here and see where does that take us. S is fixed, right? And this pi for that matter is okay, pi can be dealt with easily. So S minus pi R square is what I get, and this is equal to pi R times under root of H square plus R square. Let's see. Can we square this? Yes, maybe. This is s square plus pi square r power 4 minus 2 pi s r square is equal to pi square r square times h square plus r square. If you observe, everywhere you have r square, and this pi square r power 4, pi square r power 4 will get cancelled. And that's the important thing that happens over here. This is s square plus 2 pi s, and this is r square, by the way. This is not pi square. This will be r square. 2 pi s r square. This is s, capital S, is equal to pi square r square h square plus pi square r power 4. This goes, okay, and therefore can we observe that we have this term and this term both contain r square. Yes, so s square will be equal to 2 pi s plus pi square h square and a r square outside. Yes, and with this I can eliminate r square easily in this formula over here. Therefore v in terms of h will be equal to what? Pi by 3. We have h and then we have r square, which is s upon 2 pi s plus pi square h square. Okay, now that is the expression that you get in terms of h. Volume in terms of h is this, and after this only some differentiation remains. Maybe you can cancel out a pi. You have s upon 3 times h upon, if you take out a pi, what remains is 2s plus pi h square. This is what remains, right? And let's differentiate this with respect to h now. So v prime in terms of h will be equal to s by 3 remains outside, and denominator squared, denominator times derivative of numerator 2s plus pi h square times derivative of h, which is 1, minus h times derivative of this, which is 2 pi h. This is what you get. So this is 2 pi h square, pi h square. This actually becomes in the numerator s by 3 is okay. This in the numerator will become 2s minus pi h square over the denominator squared. Denominator squared, right? There's a huge quantity in the denominator, but the square will be there. Okay, and derivative, once you reach this stage, so we can say that h square is 2s upon pi. Okay, and that's the critical point. What happens? Show that semi-vertical angle of right circular cone of given surface area. If the surface area is fixed and let's say we increase the height, okay, if we increase the height, then the radius will have to be reduced. So in that case, volume will be 0. Volume will not be maximum, volume will be 0. So one extreme, volume will be 0, right? So if we increase the height a bit, so that particular value of height that we are getting is that critical point at which the volume will be maximum, right? Since at a different value of h, you get volume 0, that will imply that for this particular value of h, volume will be maximum. So therefore, h square is equal to 2s upon pi is important, and this gives me maximum volume. That's the important observation that you have. Although you can differentiate again and talk about it over here, you can differentiate this again and maybe see isme what you're getting is a maximum volume, this downward facing parabola kind of a thing. Yes, but this is also sufficient by simple common sense analysis of that, right? So h square is equal to 2s upon pi, but are we interested in this h square? No, we are supposed to find r as well, and then we are supposed to find sine inverse, that theta. Theta is important for us. So with the help of this h square, can we find this r square somehow? Okay, we'll find r square first and see where does that take us. So r square is equal to what? This is equal to s upon 2 pi s plus pi square times s square, h square is 2s upon pi. This is pi 2s, which is 4 pi s, s upon 4 pi s. This implies r square will be equal to 1 upon 4 pi. Okay, and this is the value of r square. This is the value of h square. But what are we interested in? We are interested in that semi-vertical angle theta, and theta can be found with the help of this h and r directly. What do we have over here? H square is 2s upon pi. This is 1 upon 4 pi. Okay, did we make a mistake somewhere? This is s. Can we eliminate that s somehow? No. Okay, so this is okay. This S will go, that's okay. This is 1 upon 4 pi. This does not fit dimensionally, right? There should be a S somewhere over here. And yes, this is wrong. So, oh, there is S square, and this should be S square actually, right? Please make that correction. This should be S square. This should also be S square, and therefore this should be S square, and this should be S square, and this is 2S minus pi h square. So h square value will not change, but then r square will be equal to this S square upon this. Okay, please make that correction. This is 2 pi s plus this, and this here is S square. Therefore, yes, we have a S in the numerator as well. Okay, now it's okay. A long question, but yes, this is important. So, r square is obtained, h square is obtained, and can we find r upon h? Yes, therefore, r upon h will be equal to what? R upon h, the ratio of this and this. What will that be? Squared, r upon h squared will be equal to what? This will be equal to s upon 4 pi, and in the denominator we will have 2s upon pi. Okay, now the s will get cancelled. Yes, the pi will also get cancelled, and what will remain is 1 upon 6. This is r upon h whole squared, and what is r upon h after this? This is 1 upon root 6. This is actually r upon h is, you can observe, this is tan theta is 1 upon root 6. Tan theta is 1 upon root 6. So what will be the value of sin theta on the basis of this? Can you deal with sin theta? Yes. Okay, this is not 6, this is 4 times 2, 8 actually. Okay, why are we making mistakes? This is 8, this is not 6, this is 8 actually, right? This is 8, this is 8, so this is 8. If tan theta is 1 upon root 8, so can we deal with over there? Yes, or here only. You have 1 upon root 8, which is 2 root 2. This will be 3. So in case this is theta, sin theta will be equal to 1 by 3, or theta will be equal to sin inverse 1 by 3. That's the complete proof of this one, right? You can handle that. Last step on your own maybe, but that's the complete proof. As you can see behind me over here, small error, please correct that, and that's a complete solution for this question. This is question number 26th for you. A very interesting, important one. Mind you, the important thing that was here was this. You should not begin with theta directly. One of the ideas could be, since you are supposed to find theta, why not begin with writing volume in terms of theta? If you do that, it will be very long, right? The calculations would be very long. These are also enough long calculations, but then if you can imagine, on taking theta as the parameter, you'll have even longer calculations. But here, this is the complete solution of this question number 26th for us. Question number 27 says that the point on the curve x square is equal to 2y, which is nearest to the point 0, 5 is which of these points, right? So one of the approaches, since this is an objective question, what you can do is, we can check whether these points lie on this curve x square is equal to 2y, that's the first thing. And then the next thing is, which of these distances is smallest? That's what you can do for the objective approach. That's not what you're looking at, right? So the point on the curve, this is the curve, let us say x square is equal to 2y, and this is a point, let's say 0, 5. Any point on this q, x, y will be at a certain distance from this, okay? And we are supposed to minimize this distance, pq. So pq square can be written very easily. This is x square plus, yes, this is what I can write as, yes, okay. This is x minus 0 whole square, y minus 5 whole square. And x square is also equal to 2y, since this is lying on this. This is 2y. This is what you have. Right, can I rearrange this? This is y square minus 10y plus 2y is minus 8y, and plus 25 is what I get, right? This is pq square, which is actually the distance squared. Okay, let's call this d. And derivative of d with respect to y will be 2y minus 8. And equal to 0 will tell me y equals 4 is the required critical point. Y is equal to 4 is where the required critical point lies. For y equals 4, x square will be equal to 8, and that tells me x square, x will be equal to 2 root 2 or minus 2 root 2. This is what you have. The point on the curve, this, which is nearest to the point 0, 5 will be which? Okay, this is one point, this is another point. So 2 root 2, 4 is one of the points, and minus 2 root 2, 4. Which of these will have minimum distance? Can you please identify that? Yes, by the way, we have only one of these options over here. But then we haven't proved yet that this is the minimum distance. y equals 4 is the critical point. For y greater than 4, this is positive. For y less than 4, this is negative. 4 is the critical point, positive, negative. So this is decreasing and increasing. So for this, yes, the distance will be minimum. But which of these is the correct answer? Maybe if you will draw the diagram, you'll get that maybe the distances are same for both of these. As you can clearly observe that x square will be minus 2 root 2 plus 2 root 2 square will be same. The distances will be exactly same. So which of these answers is correct? This is the answer which is correct, option A. If you had minus 2 root 2 comma 4, then that would also be correct, right? That's what you observe. The distances will be exactly same for 2 root 2 comma 4 and minus 2 root 2 comma 4. The correct answer over here is option A for this 27th question. The 28th question say, for all real values of x, the minimum value of this. Okay, this is a quadratic upon quadratic. We can handle this in multiple ways, but since we are dealing with application of derivatives, let's try to use application of derivatives. The minimum value of this, okay, let's call this y is equal to 1 minus x plus x square over 1 plus x square, okay. And what's the first thing that we want to do? We can differentiate this, right? We can differentiate this and see where does that take us. Oh, differentiation would be pretty long for that matter, but can we simplify the differential somehow? Maybe. We can write it as y is equal to 1 plus x square minus 2x in the numerator, and this becomes 1 plus x square in the denominator. This becomes y equals 1 minus 2x upon 1 plus x square. And now differentiation will be relatively simple, right? Okay, can we do one more thing? Yes, I can do one more thing. I can divide by this x, this becomes 1 by x, 1, and this becomes x. That is something which also can be done. Y equals 1 minus 2 over, this is 1 by x plus x plus 1. Plus x plus 1 is what I get. Okay, now this becomes even more simple. This is the case when x is non-zero, right? For x equal to 0, you'll be getting y equals 1. We can identify that simply later. So y prime is equal to what? Derivative of 1 is 0. And derivative of 2 upon something. 2 upon something would be, 2 upon x is actually there. 2 upon fx, that will be minus 1 upon that something squared. Okay, so this becomes plus 2 upon that something squared, and the derivative of that something is important. What's that? 1 derivative is 0, x derivative is 1, and 1 upon x is 1 minus x square. This 1 upon x square is what I get. Okay, and this becomes 2 times x square minus 1 upon x square times this whole thing, which is 1 by x plus 1 squared. This is what you have, right? So we can multiply this x inside, and we can simplify this further. Basically, this will convert to 2 times x plus 1, x minus 1 over here, and in the denominator what you'll have is 1 plus x square plus x and its square over here. That's what you'll get, right? Which is pretty simple. 1 plus x square, right? That's the denominator in the here. Okay, and now I can analyze the sign scheme of this particular derivative. The critical points are minus 1 and 1. Those are the critical points. For greater than 1, this is positive, here it is negative, here it is positive, and the function will increase, decrease, and then increase. We are interested in the minimum value of this function. The minimum value, the local minimum occurs at this point, or for some value over here. What's that? Since the function is increasing, the minimum value may occur here as well. Okay, after that function increases, then it decreases and it increases further. Right. So minimum value can occur at an extreme over here. And what is that extreme over here in this direction? The extreme over here is actually minus infinity. So we are interested in two values, y for x equal to 1, that is one of the possibilities, or y when x tends to minus infinity is the other thing that we are interested in. If x tends to minus infinity, okay, or x tends to infinity, do you observe that this x square is important, right? The ratio of x square's coefficients will be important. This is equal to 1. For x equal to 1, what do you get? This becomes 1 minus 1 plus 1 upon 1 plus 1 plus 1. What is that? This is 1 upon 3. Okay, this is a smaller. So this is the minimum value of this function, which is option D. That's the correct answer for this question. Question number 28. That's the correct answer for this one. Question number 29 says the maximum value of this expression for 0 is less than equal to x is less than equal to 1 is. Let's talk about this expression. This is x times x minus 1 plus 1 and whole power 1 by 3 is what we are interested in. 0 is less than equal to x is less than equal to 1. Okay, and we are interested in the maximum value of this function. Can we deal with this? Yes. We can find derivative 1 by 3 times this whole bracket raised to power minus 2 by 3. And what's the derivative of this function which is inside? This is actually x square minus x plus 1. X square, the derivative is 2x, minus x, the derivative is 1, and 0 for that one. This is what we have, right? And 2x minus 1 is important, okay? And the critical point will be 1 by 2. Okay, these are the two extremes, 0 and 1 are the two extremes. And beyond this, since this is a positive quantity, this is positive, this is negative, this is decreasing and increasing function. Now, what are we interested in? Maximum value. We are interested in the maximum value. So max 1 by 2, at 1 by 2 will get a minimum value. Maximum value will be at this extreme or this extreme. We will observe that 1 is also included, 0 is also included. We are interested in f of 0, f of 1. Y is equal to f of x, and we are interested in f of 0, f of 1. Okay. F of 0 is 0 plus 1. This is 1 power 1 by 3, which is 1. Okay. Or f of 1 is again, this is 1 power 1 by 3, which is 1. Okay. And this is the maximum value. Yes, that is the maximum value for this one over here. The minimum value can also be found at 1 by 2. This is 1 by 2, 1 by 2 minus 1 is minus 1 by 2, minus 1 by 4, 1 minus 1 by 4 is 3 by 4. 3 by 4 power 1 by 3 would be the minimum value. That's not what we are interested in. We are interested in the maximum value. And yes, the maximum value is 1. The correct answer is option C that you have over here. With this, we come to the conclusion of this exercise number 6.5 from the chapter Application of Derivatives. A big exercise based on concepts of maximum, minimum, local minimum, global maximum, global minimum, and quite a few interesting word problems based on further applications of these concepts of maxima and minima. That's the end of this big long exercise. One more exercise remains. Till then, all the best.